Okay, here is your second video of our notes. This is over the limit laws. These are ways that we can manipulate some of our limits and break them down to help us calculate them algebraically. Some of them are going to be really obvious, some of them maybe not so obvious. Okay, so in your table of contents, go and put limit laws in there. This is still standard L2. This is on your page 18. It says the target says students will apply the limit laws using known limits and graphs to determine the limit of a composite function. So on the next page right here, underneath this is all of the actual limit laws. So there's a whole bunch of different ones. We're going to go through all these and what they actually mean. The first one is what we call the scalar multiple law. And it says that if we have a coefficient in front, we can actually move that coefficient outside of the limit process and evaluate it last by evaluating the limit first and then multiplying it by whatever that coefficient is. We do this all the time with functions. Think about 3 square roots of x. If we think about that, we do the square root of x first, which is the operation, and then of course we come back and multiply it by 3. So it's the same rule, but specifically for limits. Sorry, I didn't say above. These laws, of course, can only be applied if the limit exists in the first place. If one of the limits does not exist, the law does not help us to evaluate the limit. If one does not exist, the entire composition of it will not exist. It says let b and c be real numbers, and that just means that they are values. And let n be a positive integer, just meaning a positive number. And let f and g be functions with the following limits. The limit of as x approaches c of f of x is equal to L. The limit as x approaches c of g of x is equal to k. We're just going to use those as placements for our rules. And then we're going to do an example, and it says for each of the following examples, the limit as x approaches some value, c, of f of x is equal to 4, and the limit as x approaches c of g of x is equal to -5. Okay, so for example, that very first one, the scalar multiple, this rule says that we can take, let me get a pen, we can take that -3 outside of the process. That's x is approaching c of g of x. And then we can evaluate what g of x above. We know that that g of x is equal to -5. So of course this would be equal to a positive 15. Okay, so that's kind of what that rule says. The sum and difference rule just says that if we have a subtraction or addition of multiple functions, that we can actually evaluate them independently, each on their own, and then just add what their limits are at the end. We kind of already do this algebraically by plugging in and then adding up those values. So for instance, this particular one says the limit as x approaches c. Sorry, I'm getting the hang of this. Of f of x, and because this is a plus, we're going to add the limit as x approaches c of g of x. And all that means is we already know that the limit of f of x on its own is 4, plus the limit of g of x was happened to be -5. And then, of course, if we add those, -1. That's kind of it makes sense that that rule is that rule, but it will help us when we're talking about some composite functions later. Product rule says that if we have the product of two functions, we can evaluate the limit of them independently and then come back and just multiply their limits together. So for instance, if we take the limit as x approaches c of f of x, the limit as x approaches c of g of x independently, and then come back and multiply those together, we'd get, of course, we know f of x is 4, we know g of x is -5, and then we get the overall is actually -20. Ooh, I did not mean to do that. Let's undo that piece. Oh, I keep doing that. Okay. I will get the hang of this, I promise. Let's get that arrow on there. That's what it was. Let's arrow that up. There we go. Sorry, I'm getting the hang of this new contraption for myself too. Okay, so the quotient rule says that if the limit of f of x and the limit of g of x, of course, exists, and that the limit of g of x is not equal to 0. That's important here because of the fact that then we'd be dividing by 0. We can look at them independently and then divide them at the end. So for instance, if we have the limit as x approaches c of f of x over g of x, we can take the limit. Ooh, that's not what I want to do. Limit as x approaches c of f of x over the limit as x approaches c of g of x. Independently, of course, we know f of x to be positive 4 from above, g of x to be negative 5. So of course, if we can simplify this, I'm just going to put my negative out in front. We get negative 4 over 5. And we do that all the time. Think about the ones that we're refactoring and canceling, where we're doing the limit piece by plugging into the top, the limit piece by plugging into the bottom, and then bringing that as a ratio as our final answer. So that's kind of what that one says we can do it. Power. This is kind of an important one because if we have a function raised to a power, so like let's say we have sine of x squared, we can evaluate sine first and then come back and square it second algebraically. Same thing goes for limits. We can do the exact same thing. We can evaluate the limit first and then raise whatever that value is to the power second. Kind of like PEMDAS when we're doing parentheses before exponents. So for instance, we can do it on this one. The limit as x approaches c of f of x raised to the 3/2. Hopefully you guys remember that notation from pre-cal and algebra 2. If we have an exponent that's a rational value, that's a fraction, that means that top number is an exponent and that bottom number is a root. Okay. So if we know the limit of f of x to be 4, okay, that's the same thing as writing the square root of 4/3. Okay. Sometimes we don't know the power and the root can be kind of, if the value is large, it can be confusing to do. But just remember that because these both are exponents, we can actually do them in any order. So I tend to do my square root first, my power second, only because the square root is going to make it a more manageable number. So we take the square root of 4, we get 2 to the 3rd power is in fact 8. If we had gone 4 to the 3rd, we would have gone 64, and of course the square root of 64 we know to be 8 as well. And then the very last one is the constant rule. It says the limit of a constant happens to be the constant itself. So if we take the limit as x approaches 4, this one's a little bit different. All we're going to do is get back 5. If we think of the graph of y equals 5, let's say that that's 5 right there. We get that graph right there. So it doesn't matter what the x value is, wherever that x value falls, that y value is always going to be 5. So that's why the limit of a constant is the constant itself. Okay, so let's look at some examples. I think I'm getting the hang of this. Okay, so we have two limits at the top. We know as x approaches 4 of f of x equal to negative 2, and x approaches 4 of g of x is equal to 3. We want to know the limit as x approaches 4 of g of x plus 3. So I'm going to use some of my rules. I'm going to make this a little bit bigger for me so we can see it. I know the font is a little blurry and I apologize for that. But I know from the rules above, or from the rules on the previous page, I can combine some of these rules, and I know that I can first split up of g of x plus the limit. Okay, that's that sum and difference rule. Okay, I know the limit as x approaches 4 of gx from above is 3. And I know that the limit of a constant, because 3 is a constant, no x variable, the limit of a constant happens to be the constant itself, and then that sum is equal to 6. Same thing here. This is a product rule, so that means the limit as x approaches 4 of x, and the limit as x approaches 4 of f of x can be held independently and then multiplied together. We know from the previous 2 days that the first step to limits is plugging in, so this is not a function itself, but I know the value, I can plug it in. So if I take x is equal to 4 and plug it into x, I get 4 back. The whole plug and chug. And then of course we know that the limit of f of x was -2. And then we multiply their limits and we get -8. C, the limit as x approaches 4. I know that one of the rules says that I can first split up my limit. That's that sum and difference rule. And then, of course, the power rule says I can square them second. So we know the limit of g of x is 3. We know the limit of f of x is -2. And therefore, we can add those together. We get 1. 1 squared happens to be 1. So our overall limit is 1. Let me, swap pages. I am going to do F, and then I'm going to leave D and E for you guys to do on your own. Okay, so F, one of the rules says that I can take the limit of the top. That's my quotient rule. Limit of the bottom. And because the limit of the bottom is in fact a difference, I can split that up too. So each one gets a limit. Okay. So we know the limit of g of x happens to be positive 3. We knew that from above. F of x happened to be, what did it be? -2. And of course the limit of a constant is itself. So we get 3 over -3, which reduces to -1. Okay. So try D and E on your own. Okay. Going to the next one, a graph. Same thing here. We've learned to find limits from a graph. So all we're going to do is apply these rules and apply what we know from limits from a graph at the same time. Okay. So this one, the first thing I'm going to do is take the limit as x approaches -2 of f of x plus, and there's that scalar. So I'm going to pull out that 5 out in the front. I'm going to pull out the coefficient outside of my process. This is going to be something we do very often in this class because it helps us break down our equations into more simple functions. Okay. So I'm looking at the graph of f of x. That's that top graph on your page. So as x approaches -2, right there, my y value is approaching 1. So I know that exists. Plus, that 5 is just a coefficient. So I'm going to pull it out. And then the g of x is the second graph. So as x approaches -2, right there, -2 right there, our y value is approaching -1. And of course, 1 minus 5 gives us -4. Okay. I'm going to leave B for you to do on your own. And then C. I know from my rules that the limit as x approaches 1 of f of x can be found on its own, and the limit as x approaches 1 of g of x can be found on its own, and of course we can multiply those independently. So if I'm looking at the limit of f of x as x approaches 1, so I'm on the first graph as I'm coming up, x is approaching 1, my y value is approaching 2. Okay. Now on g of x, if we look at 1, we see a jump there, which means my left limit and my right limit are not being equal to each other, which actually means that my g of x does not exist. And because one of them does not exist, this entire limit does not exist. They both have to exist, and they both have to have value for you to have a limit that does exist with these rules. And of course, I'm going to be due to a jump on, I want to be specific here, g of x.